Alright, in this session, we need to consider that we have a finite population case under the sample survey. In reality, in real life, actually we would be talking about the census of the population. If we collect all the data from the populations, then we would have a census. That means we have a finite number of data that we can collect from the populations. So if we're going to choose a sample from a finite population, then we can't simply apply the central limit theorem that we assume the population is infinite. So the finite population case, let's look at this example. If we have a population is 4251 with the size n equals to 4, if we look at the population, then we have the population mean 4251 adding up together divided by a population size that is 3. The true variance or the variability of our population distribution would be 2.5. Then we can make use of the formula from the population, yi minus the mean, divided by n minus 1. That is an estimate population S square. Okay, we discussed about how we apply that. But from the population, we can also have an estimation. So we can use that calculate as 3.3. Now, if we have a finite population, let's choose, we sample from the finite populations. We choose the sample without replacement from the population. Without replacement, that means we have a finite number of populations. So if we choose sampling twice with a sample size of 2 without replacement, then from the population size of 4, we choose any 2 numbers, then we would have 6 possible samples to be chosen. So either 42, 45, 41, 25, 21, 53. Then look at each of the sample, we would have the mean 3, 4.5, 2.5, 3.5, 1.5, and 3. So we would easily plot a relative histogram or a distribution of the sample mean. In this case, we can calculate the sample mean. We can calculate the sample mean average. So if we take them adding up together divided by 6 samples, the mean value is 3. So we just prove that the expected value of our sample mean is the unbiased estimator for the population mean. That equals to 3. Again, we can calculate the variance of our sample mean. In this case, that equals to 5 out of 6. So we can observe that it's quite different from the infinite population case. It does not equal to the true variance sigma square divided by the sample size n. We can't use the central limit theorem to apply for the finite population case. So why? We will discuss about that in chapter 3. But anyway, we need to bear in mind that in the finite population case, we cannot simply use the central limit theorem to describe the variance of the sample mean of sigma square over n, or we can't estimate the variance of our sample mean by just using s squared over n. We need to pay attention to that. That would involve some kind of the finite population correction factor. That we will talk about that in the chapter 3. Okay, one more revision on the covariance and the correlations. Later on in the chapters, we would look at some of the pair data. We would say that some of the pair data that could help us to do some projection or some correlations between the 2 variables, then we can make use of them to talk about as our parameter measurement for the populations. Usually an experiment that yield more than one random variable of interest, for example, we want to measure the characteristics per individual in a study. For example, we want to measure the intelligence level and the personality measure. So we can use these two variables to see how they are correlated with each other. One measurement is called the covariance. The covariance is measured as the expected value of each of the measurements subtracted to the mean and multiplied to the second measurement subtracted to the mean values. So that would be a covariance factor to measure how strong each variables depends on each other. So covariance and the coefficients of coefficients of correlations. For the covariance, the larger the absolute value of the covariance of y1 and y2, the greater the linear dependence between y1 and y2. If we have a positive values, that means if y1 increases, y2 also increases. Negative value of the covariance indicate that if y1 decreases, y2 would increase. So they go in opposite direction. This is the covariance measurement. However, an absolute measure of the dependence of the covariance is difficult. So let's say if I'm measuring the Hansen index as the y1, y2 would be the interest rate. So in this case, we can do the calculation to using the covariance to measure the dependence of the two variables. However, looking at the Hansen index, which is in the scale of 20,000 plus, the interest rate is about 2%, 3%. In this case, we can't look at the value of covariance to see how heavy or how much the two variables depends on each other. So an absolute measure of the dependence of the covariance would be measured. This is called the coefficients of correlations. So we use the covariance of y1 and y2 that we compute divided by sigma 1 and sigma 2. So divided by the standard deviation of each variable. Rho 1 and rho would be the correlation measure. However, we need to pay attention. The correlation does not imply any causation. So it is not saying that if the interest rate is rising, Hansen index is going to fall, or it is not the other way around. We can only observe they have this kind of phenomenon, but that's no causation involved. Correlation measures the strength of the linear relationship between the amount of exercise and the test score. So the correlation always goes from -1 to +1. If we have 1, if the correlation coefficient equals to 1, that means they are positively correlated. One measure is going up, the other one is also going up. If correlation equals to 0, that means there's no correlation between the two variables. If correlation equals to -1, one goes up, the other one goes down, negatively correlated. Okay, so one more thing I'd like to talk about before we end this revision is the least square line of two variables. Let's look at this example. If we can measure x with the trends or the data that we collected, and y variables, we collect a set of data. So we can assume they have a linear correlation between the two variables. Then we can make use of Excel to find the most fitted line. We call the least square line. The least square line would be founded using a line that describes the variable x and the variable y with the minimized distance of each of the point to the line. Okay, so in Excel we can use this function. So let me delete this data. So that equals to linear estimate, and highlight the y variables and the independent variable, and then we can find this would be the beta. Beta is the slope of the least square line. Then alpha would be, which is the y-intercept of this line if we extend it. Alpha would be 17.7 in this case. It's calculated by using the y bar, which is 73, minus beta multiplied to x bar. Okay, so y bar, minus beta multiply to x bar alpha. Then we have the least square line. My purpose is to look at the y value if I use the least square line to plot it. Okay, so if this is the case, rather than looking at the y value, I estimate y from the least square line. So in this case, that equals to alpha plus beta multiplied to the value of x. This y estimate is projected from the least square line. We can continue to do the same thing. That equals to alpha y-intercept plus beta multiplied to x. We keep doing that, and then we can have a set of y estimate from the least square line. Let's assume this is the true value of y, but we estimate the y from the least square line. We want to calculate the mean square. Mean square is the expected value, calculate from the least square line, minus the true value, take a square. So we are finding the absolute values from the distance of each of the y projected from the least square line to the true value of y. If we keep doing that, we can find the sum of all of the distance.